we discussed that there is a proper balance between ventilation and perfusion, which is important to ensure the gaseous exchange between the alveoli and the capillaries. So, let's look at the graph to understand this. This straight line in pink shows that the blood flow or perfusion increases while moving from apex to the base of the lung. Similarly, this straight line in blue shows the air we breathe in the alveoli, which is known as ventilation. You can see that the ventilation, showing the same trend, is increasing from top of the lung to the bottom of the lung. So, ventilation and perfusion both are lower in Zone 1 and higher in Zone 3. But do note the slope of the graphs here. Graph showing perfusion is much more steeper than that of ventilation. Can you guess the reason? Yes. This is because the effects of gravity that result in gradients in both perfusion and ventilation of the lung creates a steeper gradient for perfusion than the ventilation gradient. Now, let's have a look at the resulting curve of VQ ratio shown here in black. You can clearly observe that the ventilation-perfusion ratio or VQ ratio is decreasing from apex to the base of the lung, being highest at the apex and lowest at the base. Now, any mismatch between ventilation and perfusion will affect the ventilation-perfusion ratio. Well, I told you that ventilation-perfusion mismatch can occur due to the two factors: the physiological dead space or the physiological shunt. These, we can say, are the extremes of imbalance of ventilation-perfusion ratio. Alveoli that are ventilated but not perfused constitute physiological dead space, whereas the alveoli that are perfused but not ventilated constitute the shunt. Got it or not? Let me explain how this works. It's an important concept because it will help you understand the ventilation-perfusion mismatch in various disease conditions. Well, there are 3 zones of lungs. Let's consider the Zone 1 or apex first. You know that at apex, blood flow is reduced due to the gravitational force. For an instance, let's believe perfusion decreases to 0 due to any reason. Though alveolus is ventilated, but there's no blood available for gaseous exchange because blood flow to this area is 0. So, this is what we call physiological dead space. What happens to the VQ ratio then? Putting value of perfusion as 0, we get infinity. So, ventilation-perfusion ratio is increased to infinity. This is what happens in pulmonary embolism, which can result from a deep vein thrombosis, as known as DVT. This is a blood clot in the legs or arms that travels to the lungs. What happens is that the clot occludes the pulmonary artery or capillary, like this. So, blood cannot reach this alveolus. Blood flow, hence, perfusion is decreased to 0. Therefore, no gaseous exchange will occur here, though the alveoli is ventilated, as air is flowing into the alveoli. But, as no gaseous exchange is occurring here, so we can say that this ventilation is wasted here. But still, there are millions of alveoli where air can enter and carry out the gaseous exchange. Oxygen from the alveoli will not be able to enter the blood, and carbon dioxide from blood would no longer enter the alveoli to be exhaled out. So, partial pressure of carbon dioxide will be decreased in alveoli, while partial pressure of oxygen is increased in the alveoli. But do remember that the ventilation-perfusion inequalities affect the partial pressure of oxygen more than the partial pressure of carbon dioxide. The possible reason for this is that carbon dioxide is much more soluble than the oxygen. Well, high ventilation-perfusion ratio is also seen in emphysema, where there are damaged alveoli and damaged pulmonary capillaries supplying the alveoli, causing a decrease in blood flow or perfusion. Now, on the flip side, ventilation-perfusion mismatch results in a shunt. Shunt is the opposite of what we just discussed, the dead space, if alveolar capillaries are perfused in an area of the lung that is not ventilated. For example, when an airway is blocked, a physiological shunt is present. Due to an obstruction in the airway, airflow to the alveolus is decreased, but the blood flow is normal. Means alveolus is adequately perfused. Still, gaseous exchange is not possible because adequate air is not present in the alveoli for exchange. So, we can call it as wasted perfusion, just like we saw wasted ventilation in the case of dead space. Let's say the airflow, hence ventilation, is decreased to 0. Let's see what happens to the ventilation-perfusion ratio. Putting the value of ventilation as 0, we get VQ ratio of 0, exactly opposite to the dead space, where ventilation-perfusion ratio is increased to infinity. So, in other words, blood flowing past poorly ventilated alveoli doesn't pick up additional oxygen. Now, this poorly oxygenated blood returns to the heart and mixes with oxygenated blood coming from other areas of the lungs that are ventilated. This mixture lowers the total oxygen content of the arterial blood. What happens as a result is, of course, hypoxemia. Now, the larger the shunt is, the lower will be the oxygen content, and more will be hypoxia. So, physiologic right-to-left shunts may occur if perfusion reaches areas of the lungs that are not ventilated. Well, we don't want perfusion to be wasted, right? So, our body acts in a smarter way to tackle this. What it does is that it prevents the blood from entering the poorly ventilated areas of lung. It does so by constricting the intrapulmonary arteries in response to alveolar hypoxia, while it diverts the blood to better oxygenated lung segments. This ensures an efficient gaseous exchange, thereby optimizing ventilation-perfusion matching and systemic oxygen delivery. Now, this happens in various diseases, like pneumonia, where consolidation occurs. Well, consolidation occurs when the air spaces of the lungs are filled with something other than air, like dead cells and debris, forming pus. So, as a consequence, airflow in the alveoli, hence ventilation, is decreased, while the perfusion is adequate, thus decreasing the ventilation-perfusion ratio. A decrease in VQ ratio is also observed in COPD, or chronic obstructive pulmonary disease. It impairs the airflow with little effect on pulmonary blood flow, resulting in low ventilation and nearly normal perfusion. So, the overall effect is a decrease in VQ ratio. Now, another example is pulmonary edema, where there is a fluid buildup in the alveoli of the lungs. So, again, a decreased ventilation with a normal perfusion. No gaseous exchange, resulting in a decreased ventilation-perfusion ratio. So, that was about ventilation-perfusion ratio and ventilation-perfusion mismatch. For a quick recap, V by Q is known as ventilation-perfusion ratio. V refers to the ventilation, which is the airflow through the alveoli, while Q refers to the blood flow through the alveolar capillaries, as known as perfusion. Both increase from apex to the base of the lung, but the change in perfusion is a lot more than that of ventilation, and this causes a higher ventilation-perfusion ratio at the apex and a lower ventilation-perfusion ratio at the base of the lung. So, gaseous exchange, being more efficient in apex, causes an increased partial pressure of oxygen there, while a lower partial pressure of carbon dioxide. In contrast, at the base of lung, gaseous exchange is less efficient. Partial pressure of oxygen is low, and partial pressure of carbon dioxide is high. VEQ ratio, being highest in Zone 1, is 3. Ventilation and perfusion are equal in Zone 2. So, V by Q ratio is 1. And it has the least value in Zone 3, that is 0.6. Normally, VEQ ratio is 0.84, while the ideal scenario is 1. V/Q mismatch occurs in various diseases. Ventilation without perfusion is dead space, while perfusion without ventilation is shunt. That's all from my side. If you are following this respiratory series from the very start, I am pretty much sure that you have a sound knowledge of respiratory physiology till now. Do find more exciting content of physiology only on sqadia.com.
Explore our extensive library of over 1,800 video lectures to learn about a wide range of topics. Only on sqadia.com.